Derwent has carried Derby on its banks for nearly 2,000 years. The Romans crossed the river here. The first stone bridge spanned it in the 13th century. When the old St. Mary's Weir was demolished, the pier foundations were uncovered. The medieval bridge chapel, one of the very few in England, where the traveller prayed for a safe journey to faraway Nottingham, reminds us how long this place has been a vital traffic centre in the North Midlands. Its strategic placing has made Derby into a prosperous industrial and market town of nearly 250,000 souls. But it brought problems too. Eight major roads, including the A6 London to Glasgow route and 3 other trunk roads, all converge on the town centre. Life for shoppers and other pedestrians was becoming intolerable. Through traffic was impeded by bridges quite inadequate to meet the demands made on them by modern conditions. The problem was compounded by heavy local commuter traffic to and from the industrial areas. It's ironic that these industries include the building of 200-mile-an-hour trains and the world's leading aero engines. In 1964, the Town Council clearly saw the need for a comprehensive approach, and accordingly, it adopted a scheme put before it by the borough engineer. The scheme provided, amongst other things, for an inner ring road, with its northern and eastern sides built to near motorway standards. The northeast quadrant was in fact the most urgently needed section, for it would divert most of the flow from the A6, the A52, the A38 and A61 routes away from the heart of the town centre. The first stage of St. Altman's Way was opened in January 1969. It's with the second stage that we are concerned. The contracts provided for grade-separated dual carriageways crossing the river near the old St. Mary's Bridge, a 3-level interchange, a further river crossing to the south, replacing the old Cattle Market Bridge, a railway bridge, and all the spur roads and ancillary works necessary for such a radical realignment. Once the Department of the Environment had agreed the £5 million scheme, the intense labour of preparation began. Land acquisition, design, surveying, etc., etc., etc. Several weighty tomes of drawings, conditions of contract, specifications and bills of quantities were sent out to 9 major British contractors. And on the 27th of January 1970, the first citizen of Derby gave the successful tenderer a ritual start. The length of the entire site was only 3/4 of a mile, and there were no earth-shaking engineering feats involved. But within that 12-minute walk were crammed enough problems to make it an object lesson in design and construction techniques. Take, for example, the underpass which bears the westbound carriageway from Nottingham below ground level for 200 metres. Below surface layers of silt, there's a stratum of coarse, water-bearing gravel between 2 and 5 metres in thickness. Below this lies a massive bed of Kuiper marl, which is practically impervious to water. It's worth noting that before any building could take place here, the ground water level had to be lowered 1.7 metres by the insertion of well points connected to a large pump. The engineers decided that the underpass would be built as a watertight trough, a kind of concrete boat. Such a boat would, of course, float were it not anchored to the marl below. So, anchored it was. 2 rows of holes were drilled, each up to 13 metres deep, and each under-reamed up to 3 times to give good resistance to pull-out. Steel strands are inserted into the base and grout is pumped. are then stressed. And the two-lane roadway is now firmly secured. Finally, the well points are removed and the water returns to its original level. Water was a problem at Meadow Road too. Here, the road had to be realigned nearer the Derwent. Indeed, the plan called for it to project well beyond the existing river wall, and a new one had to be built. At the same time, the road was lowered by 4 meters, so that future access could be made to a projected car park. River and groundwater is excluded at Meadow Road by a cut-off wall constructed by the bentonite process. A trench is excavated and guide walls are constructed within it. Bentonite mud is then poured in to prevent the sides of the trench collapsing. Steel stop ends prevent the bentonite from flowing away. A reinforcing cage is lowered in and concrete is placed. The bentonite mud is pumped away for recycling. The resulting wall, founded in the impervious marl, cuts off virtually all water entry. An interesting glimpse of 18th century Derby was revealed in this area when an old lock was uncovered. It appears that Benjamin Outram, who built the Derby Canal in 1796, used the Longbridge Weir to raise the river level, enabling barges to be towed across. A culvert inside the weir was used to carry the canal water. The boats were hauled by horses from the now demolished Long Bridge. On the south side of the river, the Holmes Aqueduct carried the canal over a mill stream. Unfortunately, it had to be demolished to make way for the new construction. It was fitting that a section of the old aqueduct, the first of its kind in the world, was lifted out for preservation in Derby Museum. Perhaps the most dominant feature of this section of the Ring Road is the number of bridges, 13 in all, including the river crossings, which are the biggest. The Causey Bridge sweeps the road across to the north, and Holmes Bridge carries it back again further south. Great attention was paid to aesthetic considerations in these bridges, and designs were submitted to the Fine Arts Commission for approval. Holmes Bridge was the first to be built and took just over a year. The River Authority wouldn't allow permanent piers in the Derwent, so the central span of the two-span structure is apparently supported on the river wall. In effect, a temporary bridge was erected, consisting of cased piles driven into the riverbed, on which the formwork was constructed for the bridge proper. Protected by a cofferdam, carpenters erect the formwork to the pile cap for the central pier. The steel fixers place the reinforcements for the pier, and eventually the great V of the pier itself emerges. This mass of webs, reinforcement and formwork shows something of the complexity of construction. The concrete bridge deck is a continuous, pre-stressed cellular box girder. The Causey Bridge to the north had to stand comparison with its older sister, St. Mary's, and at the same time not impair too much the view of those dignified Georgian arches. To this end, the centre span has been kept as slender as possible by the addition of outer spans. They are concealed behind the wing walls. The result, a new and intriguing riverscape. The railway bridge was another interesting engineering exercise. It had to carry the main London line over the new Nottingham Road spur. The railway obviously couldn't be closed for any long period, so the bridge was built alongside the embankment and slid into position, all 6,000 tons of it. A series of box units was pipe-jacked through the embankment to provide both a foundation and a slide path for the bridge. legs was cast in one operation of 24 hours, during which 1,050 cubic meters of concrete were placed. The cantilevers were cast on subsequent days, and the whole deck was then stressed. At 8 p.m. on Good Friday 1971, the complex operation began, with the removal of 9,000 cubic meters of embankment. The tops of the box units were removed, and by 6:20 on Saturday, all was ready for the big slide. Each portal leg was mounted on 8 sledges, pulled along the sliding strips by powerful towing equipment designed and built by the main contractors. From the cabin on the bridge, the engineers monitored the inch-by-inch movement of the huge structure by means of closed-circuit television. 28 meters in 4 hours and 10 minutes will probably be the lowest speed ever recorded on this section, but on this occasion it was quite fast enough. Once in position, the bridge was jacked out to remove the sledges, then lowered and bedded onto the prepared bases. The bridge was already complete down to handrails and one section of track. British Rail completed the laying of the other 3 tracks, and on Easter Monday at noon, the first train rolled onto the new bridge. A fine example of engineering skill and precision, carried out with minimum inconvenience to the public. The matter of convenience to the public is important. As well as keeping to his schedule, and this one was completed on the date originally planned, with all the minutiae of measurements and materials, the contractor has to keep in mind that he is working in a living community. That means, amongst other things, facilitating the flow of traffic, of all kinds, and growing all the time. Consider too the complexity of surveying, maintaining and realigning the telephone, electricity, gas, water, drainage and sewer services while all this was being built. No, the apparent chaos of Derby's centre in 1970 and 71 concealed a concerted order. And as the details fit into place, as the bridges receive their facings, as the grit blasting seeks out the texture in the concrete, and the new river walls show handsomely in their Derbyshire gritstone, as the final layers of road surface are rolled down, and the Parks Department move in to clothe it all in colour, then a new light is shed on the scene. Derby has not only an efficient new road system, but a new townscape as well, full of the graceful curves and functional lines of modern engineering design. With the relief of the through traffic, life for the pedestrian in the town centre has greatly improved. And in one or two of the narrower streets, motor traffic has now been completely prohibited, except for loading and unloading every morning. Relieved of the clutter on its banks, the River Derwent becomes again the focal point of the town's life and